Hello, everyone. So today we're going to continue on our study of the previous unit by looking at rational expressions and how we can use things like greatest common factor and so forth to simplify things. We're going to be starting to get into some more complicated looking equations to solve, but once again, when we stop and think about them, we'll realize they really aren't that bad. There's many things we can do to simplify them and make them easier to work with. So let's start by reviewing rational numbers and rational expressions. So what is a rational number? A rational number is going to be something like say, for example, the number 2. Any whole number is going to be a rational number. 2, 10, 6, 15, anything. Why is that? Because when I write, say, the number 2, that technically speaking is considered 2 over 1. If I say 10, that is equal to 10 over 1. The number 1/2, this is a rational number right here. The number 1/4, this is a rational number right here. What does it mean to be rational? Basically means that the number itself, 2 or 10 or 1/2 or 1/4, can be expressed as a fraction of two different whole numbers right here. That means by definition, any whole number is going to be rational because it's just itself over 1. Any fraction like this is rational because when I have a fraction like 1/2, that is just 1 divided by 2, or I have 1 divided by 4. So these are called rational numbers right here. There are such numbers that are irrational, that is to say they cannot be expressed as one whole number divided by another. We'll get into those later. That'll be for a different unit. And just as surely as we have rational numbers, we also have rational expressions. That is to say we have algebraic expressions like something like this. 2x squared is an expression right here, and it's an algebraic one. Why? Because it has a variable in there. This is rational because I could simply write this as 2x squared divided by 1. Anything divided by 1 is just itself. Another example of a rational expression would be something like this: 10x to the 4th divided by 5x squared. I have one expression divided by another expression, so this is going to be rational right here. And it's on things just like this that we're going to focus in today's lesson. Whenever we have something like this, I have numbers in both the numerator and the denominator, and I have x's in both the numerator and the denominator. So this looks like it might be a little bit difficult to work with. But by stopping to look at it, I realize there's some things I can actually do to simplify this right here. And simplifying this is going to be the main step we do whenever we want to later take these expressions and start solving equations with them. We're going to take a hard-looking problem and make it into an easier problem. So let's take a look at this, for example. Let's always separate your variables and your whole numbers. So first, let's look at the whole numbers. My whole numbers are 10 divided by 5. And secondly, my variables are x to the 4th divided by x squared. So looking at my numbers first, 10 and 5. These have a greatest common factor, of course. The greatest common factor is 5. I could, of course, just take 10 divided by 5 and get 2, of course. Or I could recognize that they have a greatest common factor of 5. 5 divided by 5 is 1, and 10 divided by 5 is 2. 2 divided by 1, still 2. So same difference either way. Doesn't really matter how I want to choose it. But I can take 10 divided by 5 here, and I will get 2 for that. And next, I look at the greatest common factor of x to the 4th and x squared. The greatest common factor of those two is going to be x squared, of course. So x squared divided by that greatest common factor of x squared is just going to be 1, and x to the 4th divided by x squared is going to be an x squared right there. 4 minus 2 results in a 2. So this complicated looking expression here of 10 divided by 5 and x to the 4th divided by x squared really can be expressed just as this right here, 2x squared. this is going to be a lot easier to work with than that, but they are logically equivalent. So if I am given this, there's no reason I can't work with this one right here. A lot easier to work with. Let's take a look at another example. Let's say I have 15x to the 8th divided by 25x to the 6th power right here. I'm looking for greatest common factor of my numbers and my variables. Greatest common factor of 15 and 25 is going to be 5, of course. Greatest common factor of x to the 8th and x to the 6th is going to be x to the 6th. So I will say my greatest common factors are going to be 5 and x to the 6th power right there. So if I divide both of these numbers by 5, 15 divided by 5 is 3, and 25 divided by 5 is going to be 5. X to the 8th divided by x to the 6th, well, 8 minus 6 is going to be x squared, and x to the 6th power divided by x to the 6th power is, of course, just 1. So when I multiply these two together, 3 times x squared is 3x squared, and 5 times 1 is just going to be 5. So this complicated looking expression right here really can be reduced to this much, much easier one right here, 3 this x squared. This is what I would want to work with if I were given this right here. Let's take this to a different level right now and get into something a little more complicated. Let's look at some other rational expressions right here. Let's say, for example, that we were given something like this. I have, say, x plus 5 times x plus 4, and all of that divided by x plus 5 times, say, x minus 2, or something like that. Again, this is a rational expression. That is to say, it's a polynomial divided by another polynomial right here. But I happen to notice these also have a greatest common factor, one that may be not quite so obvious as, 5 going into 15 and 25 was. But what is it that these things have in common? I notice in both the numerator and the denominator, I'm taking something and multiplying it times x plus 5. I'm taking something and multiplying it times x plus 5. Here I'm taking something and multiplying it times 5 to get this expression right here. Here I'm taking something and multiplying it times 5 to get this. So it's the same logic right here, even though it looks a little bit different. Here I have a greatest common factor of x plus 5 in both cases. So let's write my greatest common factor, x plus 5 and x plus 5. I just took my greatest common factor out of both my numerator and the denominator. And what do I have left here? In my numerator, I have x plus 4. And in my denominator, I have x minus 2 right here. So this expression right here can first be thought of as the greatest common factor divided by the greatest common factor times whatever is left right here. Now here's the reason that this is so beneficial. Let's take a look at what we reduce this to now. I have x plus 5 divided by x plus 5. Well, anything divided by itself is, of course, just 1. So these we call canceling each other out. That's exactly how we express it, but they cancel each other out. And therefore, I don't even have to worry about them. So all I have left now is x plus 4 divided by x minus 2. So this expression right here can be expressed as this much simpler expression over here. So here's our approach when dealing with polynomials like this. We're going to look in every situation for the greatest common factor and basically cancel it out of every term that contains it. Remember, it's in everything. That's why they call it the greatest common factor. In order to be a common factor, it must be in every single term. And when we find it, we're going to simply remove it from the picture. We're going to cancel it out, and therefore we get a simpler expression to work with. Let's take a look at a few more examples right here. What if I were given a polynomial like this? I have 2x squared minus 4x minus 30, and I were to have that divided by 2x squared minus 7x minus 15. My drawing there. So this looks like it might be somewhat difficult to work with right here, especially if I wanted to get to solving an equation like this. How am I going to try to work with something like this? It sure would be helpful if I could somehow simplify this a little bit. Well, a couple of things that I notice. The numerator here has the greatest common factor. All of these numbers I notice are divisible by 2. So I can, first I'll make my equal sign, and I will rewrite my numerator as 2 times x squared minus 2x minus 15. If I were to distribute that 2 times x squared is 2x squared, 2 times negative 2x is negative 4x, and 2 times negative 15 would be negative 30. And in the denominator, sadly, I do not have a greatest common factor. There's not really anything I can do right off the bat to simplify that, so I'm just going to go ahead and write it as it is. But I noticed that these are starting to look a little bit more similar now than they did at the beginning, especially because now I have a smaller number of x's in both cases, and I also, above all, have the same number here. So it seems like I'm onto something here. Basically, at this point, what I'm going to do is attempt to factor both of these things, just like we learned in the last chapter. So first, let's factor our numerator. I'm going to go ahead and write my 2, and I'll write both sets of parentheses. So I need x and x to start with, because x times x gives me x squared. I have a negative number here and a negative number here. Again, the only way to end up with a negative here is if one of them is positive and one of them is negative right here. So I need 2 numbers that could multiply to give me 15, but combine to give me 2. 1 and 15 are certainly out. There's no way they can give me 2. The only other option is 5 and 3. 5 minus 3, that would indeed be 2. Okay, so I need a 5 and a 3. The question is, which one goes where? Since that is a negative 2 right there, the negative sign gets the bigger number. The bigger number is 5, and therefore my 3 goes here. Let's double check that we're right. X times x is x squared, plus 3x minus 5x is indeed negative 2x, and 3 times negative 5 is negative 15, and then we're okay. Now in the denominator, I'm going to go ahead and write my 2 sets of parentheses. Because I have a 2x squared here, I will go ahead and write 2x and just x here. 2x times x is indeed 2x squared. But in this case, I'm going to have to be a little bit more careful right here. When I do this, once again, I need 2 numbers that can combine to give me 15 right here. That's going to be either 1 and 15 or 5 and 3. I'm virtually certain I'm going to use 5 and 3. I have a negative here. That means one of these will be positive and which one will be negative. But I'm going to have to be a little bit careful about where I place these. I need a 3 and a 5 or a 3 and a 5. It's just a question of where they go. I know that I need a 5 and a 3, but a question of where I put them. I happen to notice that if I were to put a 5 here and a 3 here, this seems like I'm onto something right here, because 2x times 5 is 10x, and if I were to take 10x minus 3x, I could get to that 7 that I needed right there. Now that is a negative 7 right there, so therefore I need a negative over here to be the bigger number, and I'll put the plus sign there. Let's double check that I'm right. 2x times x is indeed 2x squared. 2x times negative 5 is negative 10x, plus 3x is indeed negative 7x, and lastly 3 times negative 5 is indeed negative 15. So this looks like it worked okay. Now here, that I've simplified it this far, I happen to notice something. In both cases, I'm taking something times this common factor of x minus 5, so these simply cancel each other out. And I finalize this by calling this 2x plus 3 over 2x plus 3. Now notice these look like I can cancel them out, but I actually can't because this says 2 of these whole things right here. This just says 2 x's right here plus a 3. If I wanted to distribute this 2 right here, I could distribute the 2 at the top and say 2x plus 6 and leave my denominator as 2x plus 3. This would actually be a better final answer. It looks a little less confusing than this, but the point is this large and long and complicated looking expression right here can actually be expressed like this, which is much simpler and a lot easier to work with. So whenever you're taking rational expressions like this, the first step right here is always to simplify it and get it into something much easier to work with. Let's take a look at a few last examples right here. Clear what I have. Let's say that I have 25x to the 6th, y to the 4th, z to the 3rd power, divided by 50x squared, y cubed, z. What is my greatest common factor in these terms? The greatest common factor of my numbers is a 25. Greatest common factor of my x's is an x squared, of the y's is a y cubed, and of the z's is just a z. So if I divide both of these by 25, I get 1 in the numerator. I don't even need to write that, and I get 2 in my denominator. So I'll write the 2 there. If I take x to the 6th minus the 2 in my greatest common factor, I get x to the 4th. If I take y to the 4th minus y cubed, I just get a y. And if I take z to the 3rd minus z, I get z squared. So if I were to write this a little more neatly, I would get x to the 4th, y, z squared, all divided by 2. And this would be my final answer right here. If I wanted to take this a little bit further, let's take a look at another good example here. And now I have 2 polynomials right here, 2 quadratic expressions. So I have x squared plus 2x minus 3 divided by x squared plus 7x plus 12. So how am I going to go about simplifying these 2 rational expressions? I'm going to have to factor both of these and see if I can cancel something out. So let's go ahead and get this set up so I can factor it. So if I factor my numerator, I'm going to get x and x, of course. I have a negative sign there. That means 1 is positive and 1 is negative. And I have a 3 here. So the only possibility is to put a 3 in 1. So where does the 3 go and where does the 1 go? Well, my 2 there is positive, so the positive gets the bigger number right there. And in my denominator right here, I'm going to once again write x and x. And I have a 12 there, so I need 2 numbers that multiply to give me 12 and add to give me 7. That's going to be 4 and 3 right there. So now, once again, I notice something. Just like in the previous examples, I have something times x plus 3, and I have something times x plus 3. It doesn't matter that it's written on the other side. Remember, this is multiplication right here and here. Multiplication is commutative. I can do it in any order I like. So I could rewrite this as x plus 3 times x minus 1 over x plus 3 times x plus 4. Notice all I did was I reversed the order of those, and I can do that because it's commutative. Now these cancel each other out, and therefore this is just x minus 1 over x plus 4. And this would be our answer right here. So the key here is to stop and think about what we're doing and take complicated looking expressions and make them into easier ones. We're going to continue building on this throughout the next few days. So this is something to practice. I'll post an assignment with this and practice these and practice some more. Feel free to ask any questions.